Yes, welcome once again, chemistry classes. In that, already we started learning chemical bonding topics. Let's today see once again one more subtopic of chemical bonding, that is theories of chemical bonding. So topic overview, weight theories. In that theories, we have a chance to expect one question, Eamcet, and one question for JEE Mains and one question for Neet. So use my coupon. It is ACI and 10. Now our topic's main lesson is what? Chemical bonding. So already we learned this chemical bonding definition. Okay, the attraction force which hold constituents atoms together. Here see how many constituents there? Two there. They are together. How? Between them one attraction force is there. Such attraction force is called chemical bonding. Now, what are the theories explaining chemical bond? Theories like electrovalent theory. So what is the first theory? Electrovalent theory explains chemical bonding. It was proposed by Covalent-Lewis theory. Okay, it is Covalent-Lewis, the approach theory. So it is called electrovalent theory, otherwise Covalent-Lewis theory. Next one, valence shell electron pair repulsion theory. After that, VBT. VBT is orbital hybridization theory. Next, MOT, molecular orbital theory. Molecular orbital theory. So in this session, we see first VBT because hybridization is completed already in our previous sessions. So now we see the VBT introduction after VSEPR theory, Vesper theory, valence shell electron pair repulsion theory. Yes. What is valence bond theory VBT? Yes, this VBT introduced by London and Hitler. This is the primarily based on the concepts of atomic orbitals, electronic configuration of the elements. So how we can learn this valence bond theory? So this valence bond theory we can learn with the help of overlapping of atomic orbital, hybridization of the atomic orbital. As the overlapping of atomic orbitals result is formation of the chemical bond. So here the electrons are localized in the bond result due to the overlapping only. So valence bond theory describes the electronic structure of the molecules, especially how they are held and what about its geometry inside the molecule. This theory says that electrons fill the atomic orbitals of an atom within a molecule. It also states that the nucleus of an atom is attracted to electrons of another atom. Means here attraction there between the two atoms and same time repulsion also present. Now we move on and look at the various postulates of the VBT, valence bond theory. So what are the postulates? Before postulates we see once again what is the valence bond theory. Yes. Sigma and pi bonds are types of covalent bonds. So covalent bonds, they contain two types of bond. In that first bond is called sigma. Yes, second bond is called pi bond. Sigma bond, first one, second one pi bond. Yes. So the result is what? How they overlap. See, head-on-head overlap. Here see. We are showing the overlap of the sigma and pi bond. So first here two orbitals, they are in spherical shape. So they are overlapping head to head overlap. So when head to head overlap, result is what? Result is sigma bond. So here S and P between the overlap. Here also P and P, yes. So P and P orbitals, but overlap is head to head overlap. So this head to head overlap result, okay, is okay, sigma bond. What about the lateral overlap? So see here, so this also P orbital, but here overlap not a head to head overlap. This overlap is called okay, what type of overlap? It is side by side overlap. So this side by side overlap also called lateral overlap. This lateral overlap result is pi bond. So here conclusion, when orbitals overlaps, bonds will form, but that overlap decides the bond. If overlap between the orbitals, head on head overlap, head to head overlap, result is sigma bond. So first bond is called sigma bond. Second bond is due to the orbitals side by side overlap. Result is pi bond. Clear? So we got here two types of bond in valence bond theory. Now valence bond theory, so all orbit overlaps are not fruitful here. So some overlap of the orbitals negative. See this diagram here, okay, figure showing this overlap is a not fruitful overlap. This overlap is negative overlap. What about this overlap? See, this overlap is zero overlap because not formation of the bond. So what about this overlap? See, this overlap is spins, we are saying. So then this overlap is called positive overlap. Then, so here we see here three types of overlaps. All three types of overlaps are not leads to formation of the bond. Only the positive overlap of the orbitals. The positive overlap of the orbitals result is okay bond. So valence bond theory postulates. So what type of orbitals they overlap here? Okay, overlapping of two off-filled valency orbitals. Yeah. So the electrons completely filled, they are not undergoing here. Okay, overlap. So the off-filled valency orbitals of two different atoms result in the formation of the bond. So see next. The overlapping causes the electron density between two bonded atoms to increase. This gives the property of the stability to the molecule. Means, which property? The overlapping causes the electron density between two bonded atoms to increases. This gives the property of the stability of the molecule. In case the atomic orbital possesses more than one unpaired electron, more than one bond can be formed, and electrons paired in the valency shell cannot take part in such a bond formation. So these are the postulates. And next postulate, a covalent bond is directional bond. So covalent bond is called directional bond. Why? Because parallel to the region of the overlapping atomic orbitals. Here overlap is how parallel. So that makes the bond is covalent. That covalent bond is directional. So confirm what here covalent bond is directional bond. So based on the pattern of overlap, there are two types of covalent bonds there. Just now we learned it, sigma and pi bond. Yes. So the covalent bond formed by sidewise overlapping. Yes, clear. And what is the pi bond? Yes, pi bond is side by side overlapping. Yes, clear. Here, even the VBT explained the geometry of the molecules, even it has the limitations. As we pointed out earlier, nothing is perfect in a similar way. the valency bond there is also not perfect. It has its own set of limitations. They are, first one, it fails to explain the tetravalency of the carbon. First one. This theory does not discuss the electrons' energies. Means here off-field electrons orbitals they are participating, but we did not use the energies of the electrons one. And the assumptions are about the electrons being localized to specific locations. Okay, these things does not explained by VSEPR theories. Okay, so this VSP the VBT theory. Yes, so after VBT theory now we see the valency shell electron pair theory. Yes, this theory predicts the shape of the molecules and electron pairs which are surrounded by the central atom in a molecule. So this theory presented by Sedgwick and Powell, and this theory is, okay, molecule will take a shape such that electronic repulsion in the valence shell of the atom that is minimized. Yes. Now what are the main postulates of this theory? So this theory especially, okay, depends on valency electrons. So valence shell electron pair theory, yes. Okay. So and here what about the electron? What are the electron pairs there? Yeah, they repulsion also minimized. Okay, due to the geometry. Yes. So now how the repulsions present? Repulsions present first SS means s orbital repulsions. Next s orbital and p orbital repulsions, and p orbital repulsions also present. Same way, okay, lone bond pair repulsions there. Okay, bond pair, lone pair repulsions there. Lone pair, yes. Okay, lone pair repulsions also present in the molecule. But what is the highest here? So bond pair less than 2, lone pair bond pair, and highest one is lone pair bond pair. Now here number of electrons, dense areas, electron pair geometry, number of lone pairs. Yes. So again, in the case of the electron pair geometry is trigonal planar, but here, okay, one lone pair, generally no lone pairs means linear. Here one lone pair means it is trigonal planar shape. Now tetrahedral, no lone pairs means that geometry is tetrahedral only, but due to the lone pair it becomes trigonal pyramidal, and due to the two lone pairs it becomes the bent shape. Now come to the electron geometry of the trigonal pyramidal. So trigonal bipyramidal, it is without lone pair. If even one lone pair also there, so here structure becomes what? Seesaw horse. If two lone pairs, structure becomes T-shaped. If here lone pairs 3, structure isn't linear. Now for octahedral geometry, so without lone pair it is octahedral. One lone pair square pyramidal. Here two lone pairs square planar. If 3 lone pairs T-shaped, if 4 lone pairs that is linear. Means here VSEPR theory, valency shell electron pair repulsion theory, due to number of lone pairs, the repulsions increases. Repulsions between bond pair lone pair. Due to the number of lone pairs, here the original geometry of the structure was distorted. Here in the case of the linear, number of lone pairs. Okay. Then what about the shape here? Yeah, shape linear but no number of lone pairs. No distortion of the geometry. But in the case of the second one, trigonal planar is the original geometry, but due to the number of no lone pairs, the trigonal planar only. But due to at least one lone pair, here it becomes what? Bent shape. Same. Now tetrahedral. So without lone pair as usual, but number of lone pairs makes the structure distortion. Here tetrahedral trigonal pyramidal, tetrahedral belt shape. Now trigonal bipyramidal. So trigonal bipyramidal is the original geometry. Yes. So number of electrons, dense areas here 5. But here due to one lone pair it is in sawhorse. It is due to lone pairs T-shaped. Due to 3 lone pairs, structure distorted into the linear shape. And what about octahedral? Without lone pairs, octahedral. 1 lone pair, square pyramidal. 2 lone pairs, square planar. 3 lone pairs, T-shaped. 4 lone pairs, the structure becomes here linear. Yes. So this is VSEPR theory. Valence shell electron pair repulsion theory. Clear? Yes. So regarding here, any doubts for you? Valence shell electron pair. See, regarding VSEPR theory, any doubts? VSEPR theory. Clear? So after this completing the VSEPR theory, as Valence shell electron pair repulsion theory. Now, so with the help of this, how we can explain the ammonia geometry. So ammonia and H3. So ammonia, in that central atom is the nitrogen, as surrounded atoms are hydrogens. So what is the hybridization of the nitrogen in ammonia? So in ammonia, so nitrogen hybridization is sp3. So any molecule, it is in sp3 hybridization. Yes. So what about then? It's what about geometry? Geometry is tetrahedral. So the red lines outline tetrahedron, black lines show the electron pairs. Yes. But here, okay, due to this lone pairs upon the nitrogen, yes, see the nitrogen is central atom, so it has the one lone pair. Due to the lone pair, the structure is completely distorted, and it got the structure is pyramidal. Now ammonia has sp3 hybridization, but its geometry is, what about its geometry? Its geometry is not tetrahedral. Its geometry is here pyramidal. Okay, this one explained by here, okay, VSEPR theory. Why? Because here bond pair repulsion is there, BP BP. Yes. So bond pair lone pair repulsion is there, and lone pair repulsion is there, and lone pair occupies the more space of the molecule. So due to this reason here, yes. So what about the ammonia molecule shape? Its shape is not tetrahedral. Its shape is what? Okay, its shape is pyramidal shape. And same time bond angle. So what is the bond angle of the sp3 hybridized molecule? 109 degrees 28 minutes. Yes. But if see the here bond angle in the ammonia 106.7. How the geometry of the ammonia distorted from the tetrahedral, same way bond angle also decreased due to the number lone pairs and repulsions. As the link in description, Spark Store, as long-term courses, crash courses, mock test, previous year's solutions, full length test, study materials also available. Clear? And our admissions open, join now, classroom coaching offline and short term coaching timings, regular coaching also available. Our two branches, one is Narayanguda, one more is Medipatnam. And online coaching, yes. So Neet 2022, yes, online coaching, JEE Mains, Eamcet coaching, and apply coupon also, yes. Use the coupon to get the all details. And see live sessions on demand, maths on demand session, physics, chemistry also available, and daily on demand live sessions also present. And every day assignments, tests, weekend, and what about the how we have to check their pending assignment and common live sessions, and immediately you will get the student test details. So in the form of the what year grade also, A, B, C, D, E, F. Next, our methodologies. So basic concepts, there's shortcut methods, model questions, exercise questions, previous, and what about chapter-wide test, weekend test, grand test, test analysis, and highly our what about here see by Spark Academy. So highly experienced faculty, personalized coaching, process-oriented coaching, personal mentoring and doubt clarification, limited batch, and hybrid coaching, online coaching also there. And see here Eamcet previous year solved papers with solutions there. Join now Telegram link and use and see our all what solutions. As after this we see the now examples. In that now first example is, what is the first example? So first example is which of the following species contains equal number of S and P bonds? S orbital and P orbital bonds. Yes. So S P orbitals bond. The S stands for sigma. S P stands for here what? Pi bond. So we have to check here sigma pi bonds. Yes. Sigma and pi bonds in given structures. Clear? Yeah. Now, so first one C and 2. How many there here? Yes. So which of the first contains equal number of sigma? So how many sigma bonds here? 1, 2, 3. 3 sigma bonds. So how many pi bonds? 1, 2, 3, 4. So 4 pi bonds. So it is the wrong options because here they are not equal. Yeah. Next question number B. CH2 Cn2. Yes. Yes. CH. Yes. Whatever here. CH. Yeah. Bonds how many here? Yes. Now what about? Yeah. Completed. So whatever here we write. C. Yes. C. So whatever here Cl. 1, 2, 3 bonds. 1, 2, 3 bonds. 1, 2. Okay. Yes. How many hydrogens? 2. It is the structure. Now 1, 2, 3, 4, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds. How many? 2 to 4 pi bonds. Yes. Now come to this HCO3. Yes. HCO3 minus. So it is a carbonate. Yes. So here what about? Okay, now we check the xenon tetroxide. Yes. So xenon is the central atom. So it contains how many total valence electrons? 4. So here how many? Oxygen forms double bond here. Yes. How many? 4 sigma bonds, 4 pi bonds. Yes. Now what is the answer? Answer is here xenon tetroxide, because if we see the structure of the xenon tetroxide, in that xenon is the central atom, and xenon tetroxide we got here how many? 4 sigma bonds, 4 pi bonds. So how many sigma bonds here? 4. So how many pi bonds? 4. Yes. So what is the answer? Answer is here D, because contain equal number of sigma and equal number of pi bonds. Clear? So now next question. Yes, question number, which one? Yes, second one. Which one of the following molecules contain no pi bond? Yes, we have no pi bond. Now first one we see is the sulfur. Sulfur for oxygen is forming what? Yes, double bond. 1, 2, 3, 4, 5, 6. So here pi bond is there. Now come to the NO2 nitrogen. Yes. So here also pi bond present in the case of the NO2 molecule. Now CO2, yes. In the case of the carbon dioxide also pi, yes, bond is present. So what is the question? Which one of the following molecule contains no pi bond? Now we check the H2O, oxygen is the central atom, hydrogen, yes. So oxygen has 2 lone pairs. Yes, in the case of the H2O structure, yes. In the case of the H2O, oxygen is the central atom here, has 2 lone pairs but no pi bond. Only here it has the only what? Sigma bond. So answer is what? D, because D does not contain here pi bond. Yes. Clear? Now question number, yes. Which one of the following statements is not correct for sigma and pi bonds formed between 2 carbon atoms? Yes. So which one of the following statements is not correct for sigma and pi bonds? Sigma bond is stronger, yes, okay, stronger than pi bond, correct. So what is the question? Not correct, yes. Next, bond energies of sigma bond, pi bond are the order of. So they given the bond energy of sigma bond 264 and they given the pi bond 347. So bond energies units are what? Kilojoules per mole. So in that sigma is 264 and what about pi is 347. Is it correct? Because sigma bond is the strong bond. Okay, sigma bond contain, okay, pi bond it is a strong. Then for sigma bond required more energy to bond dissociate. So okay, regarding this question for this question answer is incorrect, because sigma bond compared with the pi bond has strong, so its bond energy high compared with pi bond. So in this option should be bond energy of the sigma high and bond energy of the pi compared with sigma less. Then they give an opposite direction, so it is the wrong option, incorrect. Now free rotation of atoms about sigma bond is allowed but not in case of pi bond. Yes, sigma bonds they contain free rotation around the carbon and sigma bond determines the direction between carbon atoms, but pi bond has no primary effect in this regard because pi bond is not a strong bond compared with sigma bond. So then what is the answer? So answer is B is the correct, because incorrect option they asked. So this incorrect option. Clear the answer? Yes, clear? Any doubt regarding this question? Clear this answer? Yes, now next, here we go the next question. Next question is, main axis of a diatomic molecule is Z. Molecular orbital px and py overlap to form which of the following orbitals? So question number 39. See, the main axis of diatomic molecule is Z. So Z is what? Main axis. The molecular orbital is px. Px and Py. Overlap to form of the following. So which one is possible to form here? Okay, the main axis is Z, but here, so this overlap is not a, yes, what type of overlap? Okay, this overlap is not a, what? This overlap is not a, okay, main axis Z, and what about P? Then this, okay, Px, Py, okay, overlap is not a fruitful, no, fruitful, but it is not a, okay, head to head overlap. So then this overlap is side by side overlap. So what about the side by side overlap? So P molecular orbital will form it. Yes. So answer is what? Main axis of a diatomic molecule is that molecular orbital Px, Py overlap to form which of the following orbital? So it forms P molecular orbital. Because in that S orbital is not there, D molecular orbital there, no bond will be formed also wrong. So answer is here P molecular orbital. Next, question number 40. Question number 40 is, yes, okay, which statement is not correct? Yes. So a sigma bond is weaker than a pi bond. So here what they are saying, sigma bond is weaker than pi bond. So next, a sigma bond is stronger than a, okay, pi bond. So a sigma bond is stronger than pi bond is a correct. Because sigma bond is the first bond and second bond is called pi bond. Clear? So sigma bond is called strong bond. It is stronger compared with here pi bond. Yes. Now a double bond is stronger than a single bond? No. A double bond is stronger than a single bond? Yes, because one more bond is added, that is called double bond. A double bond is shorter than a single bond? Yes, because bond length is decreasing. Yes, here. So what about not a correct statement? So a sigma bond is a weaker bond is a wrong. The sigma bond is stronger than the pi bond and first bond is sigma, that is formed by due to overlap of the head-on-head overlap. Yes. So then incorrect one, not correct one is A. The remaining B, C, A, D, B, C, D are correct. Now question number 41, yes. The linear combination of two hybridized orbitals belonging to two atoms. The linear combination of, yes, hybridized orbitals of belonging to atoms and each having one electron leads to the formation. Yes. So they have what here? S2 atoms and each having one electron leads to the formation. Yes. So what type of bond they will form here? Can they form here pi bond? Wrong. Because here the orbitals belonging to atoms and each having one electron. But that is linear combination. In that coordination covalent also? Wrong. What about double bond? Wrong. Is it sigma bond? Yes. So the linear combination of two hybridized orbitals belonging to the two atoms and each having one electron, they leads to formation of the first bond. Such first bond is called sigma bond. So already we discussed it. First bond already sigma bond, second bond only pi bond. Clear? Yes. Now next question. Question number 42. Yes. Which of the following does not apply to metallic bond? Yes. So metallic bond, actually bonds there are two types, primary bond and secondary bond. In primary bond, covalent bond is there. Okay, next ionic bond is there. Metallic bond also primary bond. So which of the following does not apply to metallic bond? So overlapping valency orbitals. As overlapping valence electrons leads to formation of the bond. So mobile valence electrons means which are delocalized. Okay, delocalized electrons, yes, they also, yes, they transfer one place to other place. So highly directed bonds, yes, highly directed bonds is not possible in the case of the, okay, metallic bond. So which of the following does not apply to metallic bond? In metallic bond, like yes, overlapping, mobile, delocalized electrons there, but highly directed bonds not present in metallic bond. In metallic bond, only one type of bond is there, that is called metal bond. So metallic bond is only contain one type of bond, that is present between the all metallic elements. So in metallic elements, only one type of bond only there, that bond is called metallic bond. Now question number next one. The angle between overlapping of one s orbital and one p orbital is yes. So one s orbital, one p orbital, one s orbital, one p orbital. Now one s orbital, now one p orbital. So what type of bond angle? Question. So what type of the bonding is question. Now see. So here overlap is there. Yes. What type of bond? This bond is first sigma bond, because only first bond. So it is sigma. So next, what about one s orbital and one p orbital? Yes. So one sp means what about sp hybridization? So how many hybrid orbitals there? Okay, two sp hybrid orbitals there. In the case of the two sp hybrid orbitals, in the case of the two sp hybrid orbitals, what about shape? Shape is called here linear. For example, we know already BeCl2. BeCl2, in that beryllium is the central atom. So beryllium atomic number, hydrogen, helium, lithium, beryllium 4. So electronic configuration 1s2, 2s2. Yes. So here, what about in the ground state? 1s2, 2s1, 2px1. So here hybrid orbitals are sp. So hybrid orbitals, how many there here? In the case of the B, sp, sp. So now, what about they overlap with the s orbital? They overlap with the in BeCl to p orbital. They are overlapping with s, overlapping with What about sp orbital? Now after overlapped B with chlorines p orbital, so what about the shape? Shape is linear. So when the shape is linear, now what about the bond angle? 180. So what about here? 180. 120 is trigonal. 109 degrees 28 is sp3 hybridization. So hybrid, the tetrahedron. Now here this one linear. So what about here bond angle? In the case of this answer, so example also we taken BeCl2. So here what is the bond angle? Here bond angle is So bond angle here how much? 180 degrees centigrade due to the hybridization of the sp. Now next, which of the following bonds will be most polar? So here bonds there. What is the first bond? Nitrogen and chlorine bond. Oxygen and fluorine bond. Nitrogen and fluorine bond. Nitrogen and nitrogen bond. So nitrogen and nitrogen bond. So in that we have to check. We have to check which is the more. Which of the following pairs common? So we have to check here. Which of the following bonds will be most polar? We have to check. Now see here, nitrogen chlorine. In that electronegativity different is there, Oxygen fluorine there. Nitrogen fluorine is there, but electronegativity different more in the case of nitrogen and fluorine, because fluorine is more En, but in the case of their En is what? Less. What about here? Less. Here more. Here what? Less. Here same, no different. So what is the then? En different more in the case of the NF. So which of the following bonds will be most polar is nitrogen fluorine bond. That bond due to the highly electronegative character different, it is showing more polar. Next question, which of the following pairs of compounds is isoelectronic and isostructure? So here what about, so they have the same structure. Now tellurium iodide and xenon difluoride, as they have the same structure, no different. Here structure is changing. What about iodine IBr to Z xenon difluoride, BeN to ZnEps? Okay, which of the following pairs of compound is isoelectronic with isostructural? So BeCl2 and BeF2. And what about here IF3 and xenon? Yes. So here answer is none here. Yes, no isoelectronic each other here. Yes. Next, dipole moment of which ketone is maximum? Yes. So what is the ketone here maximum in the case of the dipole moment? Yes, in the case of this dipole moment, okay, C, because here more dipole moment is maximum. So answer is C. Yes, subscribe our channel and press bell notifications. You will get the notifications. Yes. So every day. So in this session, okay, we learned the theories which are explained chemical bonding. Yes. So in this session we learned the theories like which one? Okay, theory number 1. First theory is called what about? First theory. Yes, electrovalent theory. Yes, this electrovalent theory is called Coase-Lewis theory. So first theory explained about the covalent compounds. Next theory is valence shell electron pair repulsion theory, and third is VBT or orbital, and in that hybridization theory. Okay, so both are same here. So molecular orbital theory is here. So in our next session we see so what is molecular orbital theory, and after completing these theories, they could not explain the bond order of the properly the molecules and magnetic behavior. So magnetic behavior, bond order, they could not explain it by above theories. But after these theories, the molecular orbital theory, so it is the last theory in chemical bonding. It explained the bond order. You take any molecule bond order explained by MOT, same time magnetic behavior, the given molecule is paramagnetic or diamagnetic, that also explained MOT. So molecular orbital theory explained bond orbitals, bonding order, bond order and magnetic behavior. Yes. So now we completed theories from chemical bonding. As these are the theories explained very well about the geometry and hybridization, bond order, magnetic behavior of the covalent molecules. And this chart is very useful for us. So according to this chart we can confirm the molecule of the structure, because see here, so here this chart explaining for us what is the geometry original, and due to number of lone pairs how the geometry is changing. Yes. So see for example here, what about here H2? So and what about here this belt shape one? Yes. So hybridization and number of electrons same, but due to the number of lone pairs only the bond angle is changing due to the changing what geometry of the molecule. Yes, by this way. So VSEPR theory is very useful to learn molecules correct geometry. So one example also we taken, that is what ammonia. Ammonia is the best example to explain it. According to the VSPR theory, what about is its geometry and bond angle. So here ammonia, even its hybridization is sp3, but it is showing different bond angle and what molecular geometry due to what lone pairs. So this clearly explained by VSEPR theory. So valence shell electron pair repulsion theory explained completely the geometry of the ammonia molecule. So what is the conclusion from this session? So from this session we concluded here VSEPR theory and VBT both theories, they explained geometry of the molecules. Clear? And VSPR theory explained here why the molecule geometry is changed. Okay, that we will get idea by the VSEPR theory, valence shell electron pair repulsion theory.